Hello and welcome back to Pegasus Rocketry. My name is Mason and I get to talk to you about the progress on my flight computer. Let's get to it. Let's start with the first topic of the day, and that is the fact that it finally talks. We have it talking.
Battery 7.93 volts. Software version 0.2. Main 500 feet. Drogue. Apogee.
Oh, isn't that so exciting? We also have it where you can change the different settings, like you can adjust the main by pressing this button.
Main 600 feet. Main 700 feet. Main 800 feet. Main 900 feet.
And you can change the drogue settings with this button.
Drogue 0.50 seconds. Drogue 1 second. Drogue 1.50 seconds. Drogue 2 seconds. Drogue apogee.
Ah, isn't that awesome? And since last time we spoke, I got a new piece of test equipment, a fun little vacuum chamber to be able to simulate flights. This is my vacuum chamber. It runs off of an automotive HVAC vacuum pump, so it can pulse a very strong vacuum. And just guesstimating off of the gauge here, I can get close to 75,000 feet worth of vacuum out of it. So we can test some really high flights with this, so that's kind of exciting. It's really straightforward. We have a vacuum line that comes in this side with a little ball valve to open or close the vacuum, and a second ball valve to open and close the intake for depressurizing the chamber. It's got a little filter on it so you aren't sucking in contaminants. So pretty decent. It holds a perfect vacuum. I'm able to string out the debug ribbon cable for the board so that I can debug it while it's under vacuum, so that's really handy as well. Let's show you what a simulated flight looks like, shall we? The lid just lifts right off. We'll take the flight computer powered up.
7.94 volts. Software version 0.2. Main 500 feet. Drogue apogee.
Perfect. And then we can set the lid on, and it's going to get loud. We'll turn on the vacuum pump and then crack the vacuum ball valve. Okay, we've hit apogee, and we can slowly depressurize.
Maximum altitude 20,926 feet. Maximum acceleration 1.16 Gs. Maximum altitude 20,926 feet. Maximum acceleration 1.16 Gs. Maximum altitude 20,000.
And we'll just repeat that until you get to your rocket.
Feet.
And so that's what a simulated flight looks like. You'll notice that the speaker's a little different. It's not the one that we initially built with. As you can see here, it's a little different. And that's because this guy here, he does not get loud enough, especially inside of an electronics bay, for you to hear. And it's not a matter of the amplifier's not strong enough, it starts clipping if you put any more power to it. So that was very disappointing and led into a whole big search for a better alternative. Here is a non-comprehensive assortment of some of the speakers that I have acquired to test and see their feasibility in order to try to find a better audio solution than the speaker that I have currently. We were getting creative with several different options. We have fun things like these audio transducers that I tried. They're not a speaker themselves, they're just like the voice coil of a speaker effectively, and you're supposed to be able to adhere these onto different surfaces and turn the surface into a speaker. I have tried this with the electronics bays and didn't have great results. That could have been fun. The best performing one is this guy, but he is way too heavy, he's way too thick, and how is that going to be mounted? That's just not feasible, but it was a good speaker. Playing with other smaller speakers, much smaller, but still on the larger side, but it does have much better audio performance than what we have here. We got some of these smaller ones. They're kind of cool, but how do you attach it? Because they have these adhesive fronts, but that would be facing backwards, and then you still have wires to solder. It gets interesting, and there's still some engineering to achieve a solution here. We've got to find something a little better. Really want to try to play with this guy, see how well he works. He's got spring contacts on the back, so on the cover plate we're going to make for this, he could just be attached to that and make contact when it's inserted. That would be feasible, but there's still some work to happen on the audio path. So that was one of the lessons learned once we got it speaking, is the speaker's too quiet and we have to do something else. Unfortunately, I have discovered a fatal flaw with my hardware. Do you remember when I first announced this project how I wanted high sample rates of the accelerometer and the gyro? I was looking for kilohertz data. I managed to capture the kilohertz data. That wasn't the issue. The problem I'm running into is when I go to write that into a CSV file after the fact. It was working fine with 10 seconds worth of data on the bench, but when I changed it to 5 minutes worth of data for actually flying, that turns into 300,000 samples. And this is where the problem lays. Now things are going to get really nerdy for a second while I explain the flash memory and why this is a problem. Here we have the flash memory. And the flash memory is broken into 1024 different blocks. And each block is broken up into 64 different pages. And each page is broken up into 2048 different bytes. We could go further, but this is as deep as we need to get. Flash memory is kind of interesting. In the erased state, all the bits are ones. And when you write to it, you can only turn a 1 into a 0. You cannot turn a 0 into a 1 unless you do a bulk erase. And on the flash that I'm using, you can't erase a byte, you can't erase a page, you have to erase an entire block all at once. So here we are with our flash, and it's fully erased. Every byte is set to FF, which is all ones in hex. And now we can write some data to bytes 1 and 2 of page 1. In this case, 01 and 02. We can make another write to page 1, this time bytes 3 and 4 with data 03 and 04. We can even make a write to page 2 with data 05, 06, 07, and 08. Now say you want to write to page 1 again. You're not allowed to until you erase the entire block 1. And if we erase block 1, we lose all the data from page 1 to page 64. So now we need to copy the data from block 1 to block 1024. And now that we have copied the data, we can safely erase block 1. And now that block 1 is erased, we can copy the data back from block 1024 to block 1. And while we do so, we can modify bytes 1 and 2. And this is the only way we can modify bytes 1 and 2 while preserving the rest of the data in block 1. And here we have copied block 1024 back to block 1 while modifying page 1 bytes 1 and 2 to AA and AB. Now on the KISS flight computer, I'm using blocks 1024 and 1023 as a buffer for copying data. And the software library I'm using to write these CSV files only allows me to write one line at a time. I can't do a bulk write. And remember, now I have 300,000 samples. I can only write one sample at a time, and I have 100,000 erase write cycle per block on my flash memory. And so now blocks 1023 and 1024 are going to get each 150,000 program erase cycles. Now this will burn out the flash in one flight. And this is why I need to redesign the hardware to incorporate something called managed flash, like an eMMC, that has a controller inside that automatically wear levels. Wear leveling is pretty cool. It's where it looks and sees that block 1024 in this example has a whole lot of write cycles, and I'm writing to block 1024 again, but it sees that block 2 has very few cycles. So it will write the data to block 2 and map 1024 to block 2. And then when I go to read block 1024, it doesn't read the contents of physical block 1024, it reads the physical block 2 and sends that back to me. And it will automatically level the write cycles to each of the blocks so that they all wear out at about the same rate. And another reason to change the hardware is because of the slow USB data write speeds, and that is because I am writing to my flash with a single data line at a slow clock speed of about 2 megabits a second. And if I increase the speed from 2 megabits a second to 4 or even more, it creates an interrupt storm that actually slows the overall throughput. And lucky for me, ST Micro has come out with a new series of microcontrollers, their H5 series, compared to their G0 series that I'm currently using, that for the same price, I can go from a 64 megahertz microcontroller to a 250 megahertz microcontroller that also has an MMC bus that also has a 4-lane data bus to talk to the eMMC. Now, considering the increased clock speed, the increased MIPS per megahertz, and the 4-lane data bus, I should be about 17 times faster than I currently am. So while it will hurt to redo all the hardware, it's going to make for a much better product in the end. Now let's take a look at an example of some of the data that I have recorded with the KISS compared to an egg timer. And here is a comparison of a 76mm piercer running a 54mm Aerotech J401, and the egg timer is in blue and the KISS flight computer is in orange, showing a delta of only 11 feet from the KISS compared to the egg timer. That 11 feet is super encouraging, especially since the egg timer runs a filtering algorithm, and on the KISS that was just the straight up raw barometric pressure altitude. I see that I have a software bug that I need to fix from when I'm in a ring buffer on the pad waiting to detect the launch to when I actually detect the launch. I see that I'm recording all basically zeros, but that'll be just a simple little software fix. In conclusion, I've got to redesign my hardware to allow my 1 kilohertz data rate, and while I'm waiting for the new hardware to arrive, I will continue to fly and have others fly to record more data with this guy. This will enable some further algorithm development.